the MAPS group, as a committee, decided that it would be interesting to have a talk on something that could become very important in the future. We want to alert you to what could happen. You're all familiar with climate change. It could be on the horizon, which is one of the causes of it is increasing carbon dioxide. But there are many other effects of increasing carbon dioxide. And tonight's talk on ocean acidification will take a look at what we are learning about ocean acidification. Anyway, over in Monterey, or actually Moss Landing near Monterey, there's the Monterey Bay Aquarium Research Institute, and they have some excellent people, and we were able to find Dr. Edward Peltzer, who's a real expert on marine chemistry, and he's going to tell us tonight about ocean acidification. Dr. Peltzer got his bachelor's degree from Bucknell College back in Pennsylvania, his doctorate from Scripps Institute in San Diego. Scripps, and then he went on to Woodsall, two of the best marine science places in the world. And now he's at another one of those great marine places over in Monterey. He worked at Woodsall back in Massachusetts for about 20 years. And then he moved on here, where he's now a senior research specialist at Monterey Bay Aquarium Research Institute. He's also the author, the editor of the Journal of Marine Chemistry. I hope I got that right. And he's written dozens and dozens of papers on the chemistry of the oceans. So he's highly qualified to tell us what's going on. Remember, this is research in progress. As you will find out tonight, we don't really know yet how much the CO2 is going to affect the oceans. We're going to find out exactly what we do know tonight. So would you please give a very, very warm welcome to Dr. Edward Peltzer.
Thank you, Steve. Well, thank you, Steve, for that nice introduction. It's my pleasure to be here tonight, and I would like to talk to you about, as Steve said, one of the other effects of adding carbon dioxide to the atmosphere, and that is ocean acidification. So let's begin with what ocean acidification is. In simple terms, it's what happens to the ocean when you add massive amounts of carbon dioxide to the atmosphere. This creates an imbalance, and the carbon dioxide is forced by chemical means into the ocean, where it reacts with seawater. And when it does that, it forms an acid that lowers the ocean pH. This is a problem that's happening worldwide, and it's because all the industrialized nations of the world are burning fossil fuels and releasing the carbon dioxide into the atmosphere. Now, to see how this works requires us to look at a few chemical reactions. So if you're the kind of person that runs screaming from the room, you might want to close your eyes for the next couple slides, but then I promise you we'll be pretty much done with that. So we begin with carbon dioxide, or CO2, reacts with water to form carbonic acid. This is an equilibrium reaction that goes back and forth. The carbonic acid quickly ionizes into hydrogen ion and bicarbonate ion. The hydrogen ion is what causes the acid. This is the acid that's formed. The bicarbonate ion can also ionize into hydrogen ion, or a second hydrogen ion, and carbonate. Now, when ocean chemists talk about the total CO2 that's in seawater, they're talking about the sum of all the species. Now, the extent that this reaction goes depends upon the pH of the seawater. If you're looking at, say, rain, for example, which is pure water, the CO2 will react with that, form carbonic acid, which would ionize to form hydrogen ion and bicarbonate, but it would stop here. If you're adding CO2 to a very basic solution, it will go all the way down the chain to carbonate. But when you add CO2 to seawater, there's already a lot of carbon dioxide there, the bicarbonate form, but some is in carbonate. So you have the first two steps of the reaction, but then some of this hydrogen ion reacts with the carbonate that's already there to form more bicarbonate. So it's not that linear chain that you might think of. It actually stops part way. And it's this carbonate here that buffers the addition of the hydrogen ion, which is the acid to seawater. Now, why this is important will become apparent when we start talking about the impacts on biology. Now, I've mentioned the term pH. Now, this is simply a measure of acidity. It was invented by Søren Peter Lauritz Sørensen, and he published his paper in 1909 on the pH scale. He worked at the Carlsberg laboratory, and he was interested in the reactions between CO2, acidity, and proteins. And he needed a way of measuring the large changes in hydrogen ion concentration that he was seeing in his solutions. Now, some of you may already know what the solutions were he was working on. You may have heard of Carlsberg beer. The brewery actually funds the laboratory and funded all of his research, and it still funds a laboratory today that does a lot of research on protein chemistry. So pH isn't quite so esoteric as you might think. There's a very important product out there that... Now in high school, you may have heard that pH is minus the log to the base 10 of the hydrogen ion concentration. When you take chemistry in college, they tell you, well, that's actually not true. It's really the minus the log to the base 10 of the hydrogen ion activity. So they put these curly brackets around it to make it different from the hydrogen ion concentration. Well, how is the hydrogen ion concentration different than its activity? And that goes by the activity coefficient. So it's just this simple expression. But what you don't see coming is they had this horrible equation for the activity coefficient. And this has been known to drive chemistry students screaming from the room. This equation here is dependent upon the ionic strength, which is the sum of the concentration of all the salts times the square of their charges. Now, this works very well for simple solutions and dilute solutions that you might have in a chemistry lab. But when you get into seawater, which is a very complex salt mixture, this equation here goes across here and around the room and out that way. It's much too complicated to solve easily, and it turns out it doesn't even work that well. So in the oceans, ocean chemists have devised a new pH scale just for seawater. They started out with the free scale where they used the minus log to the base 10 of hydrogen ion, the free hydrogen ion concentration. This wasn't quite good enough, so they added a second term, and more recently they added a third term. Now the difference here is just 1/10 of a pH unit. And the difference between these two is just 100th of a pH unit. And why I'm telling you all this is not to confuse you with these different terms, but to point out the fact that ocean chemists are trying really hard to get the pH as precisely as they possibly can. Because it's small changes in pH make for large changes in the partial pressure of carbon dioxide in seawater. Now, for tonight's talk, you don't need to remember those equations. We can go with this practical pH scale, where 0 is acidic, 14 is very basic, and 7 is neutral in the middle. Yeah. Surface seawater has a pH of about 8.1 to 8.3. Deeper down in the ocean where the oxygen minimum is, and the oxygen minimum occurs because bacteria has been eating organic matter and making CO2, the pH there is between 7.3 and 7.6, depending on where you are in the ocean. Clean rainwater has a pH of 5.5. That's because rainwater isn't buffered. So the same amount of CO2 in the air in clean water that's unbuffered gives us a much lower pH. If you've heard of acid rain, which was a problem a couple decades ago, that water was even more acidic. Sometimes it even got below 4. Because of laws have been passed reducing the emissions of sulfur dioxide and nitric oxides, acid rain isn't nearly the problem that it used to be. I'm also going to be talking about very large terms. One is called a gigaton. You probably haven't heard of this term. The numbers of, or the amount of carbon dioxide that's being released are tremendous. So we have to use these large terms. Giga means a billion, and a ton, this is a metric ton. It's 1,000 kilograms or 2,200 pounds, about 10% more than the US ton. Now, how do you picture that? That's a bigger number than I'm usually work with. Well, a liter of water weighs a kilogram. A liter of water is about a quart. If you had 4 liters, 4 quarts is a gallon. That will weigh 4 kilograms, about 8.5 pounds. But if you had a cubic meter of water, this is a cube about a little bit more than a yard on a side, and fill that up, that would be 1,000 liters, and it will weigh a metric ton. Well, now we need 1 billion of them. So now imagine this cube is not a meter on the side, but is a kilometer on a side. Kilometer is 1,000 meters, about 10% more than 1,000 yards. So imagine 10 football fields with 10 end zones running off in these 2 directions. And in the vertical direction, another kilometer. Imagine something 4 times the size of the Transamerica Pyramid in San Francisco. That's how big this cube is. And if we filled it with water, it would weigh a gigaton. So that's some idea of how big that is. Now, why is ocean pH changing? If we go back to the beginning, it actually begins with James Watt. And what James Watt did is he was one day asked to repair a steam engine that was being used to pump water out of the coal mines. This is the Newcomen steam engine. And he found it was very inefficient and very slow. So he made many changes to it and invented his double-action steam engine, which is shown here. Now, what happened was the Newcomen engine only works up and down. It's just a linear pump. It's very good for pumping water out of coal mines, but it's very hard to use that for other things. And in the 50 years that Newcomen was building these steam engines, he sold about 100 of them to the mines in England. In the 25 years after Watt built this steam engine, he and his partner Bolton sold 500 of these steam engines, not a single one to the coal mines, but he sold them to textile factories, he sold them to machineries, he sold them all over England. He even put one on top of a railroad carriage, made the first steam locomotive. And it was this one invention, because his steam engine could turn a wheel and make rotary motion, that it changed the course of human history and caused what we call the Industrial Revolution. What happened is these all ran on coal. So suddenly there was a demand for more coal, and it hasn't stopped since. Callender looked at this and realized mankind is actually changing the composition of the atmosphere, so he wanted to know what kind of impact this was. And he noticed that since 1800, mankind had been burning coal and eventually petroleum and natural gas as fast as they could pump and dig it out of the ground. In 1938, he said all that coal and all the fossil fuels, that's all been burned to carbon dioxide. Putting that in the atmosphere is changing the atmosphere's composition. It's going to have an enhanced greenhouse effect. The Earth is going to get warmer. And he actually made the first calculation of how much that would be. But the thing to notice here is he had estimated that 150 million tons of carbon dioxide, and this is 150 gigatons of carbon dioxide, was added to the atmosphere in the last 50 years. When you do the math, that's 3 gigatons a year. Today we emit 30 gigatons of CO2 per year to the atmosphere. This is 10 times what it was just 70 some years ago. So the rate of CO2 production or emission has gone up dramatically. Now he also, when he made his calculation, noticed that the ocean, because it's slightly basic, would be absorbing some of the CO2. And he said with a mixing time of 2,000 years in the ocean, he predicted what the partial pressure of CO2 would be in the atmosphere at different times. And you notice this number here. It's 3.73. In the units we use today, it would be 373 parts per million. He said it would take until the year 2200 for this to happen. Well, we passed 373 in the atmosphere in the year 2000, right there. So we're running 200 years ahead of his schedule. And he noticed that we were burning fossil fuel much faster than it was at the beginning of the Industrial Revolution. So this process of burning fossil fuels, producing carbon dioxide, just keeps accelerating. Now, there is a record that was begun in the late 1950s by Charles Keelan, measuring CO2 in the atmosphere at the top of Mauna Loa, which is a volcano in Hawaii. He went there to get away from all the local influences from industry. He also made sure that he was only sampling air when it came downslope. So it wasn't coming up from where they were burning sugarcane on the island. It wasn't air that was coming up from the town where there was cars. This was only clean air coming downslope from the top of the volcano. And he started this program. It's continuing today. This white line is the trend line. And each one of these dots is a monthly average, or a monthly sample. Now you notice a couple things here. One is, the most obvious, is this tremendous rise in CO2. If you go back a few years to 1950, you hit 310 parts per million. If we extrapolate this a few years further to about 2015, we'll hit 400. Now, 310 parts per million in 1950 was 30 parts per million higher than what we think carbon dioxide was before the Industrial Revolution. So the first 200 years of the Industrial Revolution, CO2 in the atmosphere went up 30 parts per million. In the 65 years since then, it's going up an additional 90 parts per million. That's 3 times the initial amount that took 200 years in 65 years. The rate of CO2 production from the burning of fossil fuels is increasing exponentially. The other thing you see here in this line is this sawtooth pattern. These are monthly samples. It peaks here in May of each year, and the low point is October. What we're seeing there is the effect of the plants on the terrestrial plants on the planet. They grow in the summertime and take up CO2. So from May to October, they pull the CO2 concentration down. Then fall comes, the trees lose their leaves, the grasses die, bacteria in the soil converts this all back to carbon dioxide, and the CO2 goes back up again. But each time it goes up and down, it goes up a little bit higher from the burning of fossil fuels. You also see this yellow line here. This is not a statistical fit to the data. This is a prediction. Whereas if we start at this concentration here in 1958 and add just 57% of what we think is being produced from the CO2 that's being produced from the burning of fossil fuels to the atmosphere, this is what we would get. It's very remarkable that this 57% holds constant for 50 years. There's some fundamental process here that's controlling this process. It's a very predictable fraction. So we know that if we burn a certain amount of fossil fuel each year, 57% of it is going to go into the atmosphere. But all of it is released into the atmosphere, so where's the other 43% going? Well, Callender, in his original calculation, said it was going into the ocean. So ocean chemists began looking, once they saw the Keeling curve, began looking into the ocean to see if they could find the CO2 that was going there. So the first attempt at this was done by Peter Brewer on a geosex expedition in 1972. This was an expedition where they took sections through all the major ocean basins. In this top figure is plotted the salinity starting here at about 55 degrees south, just north of Antarctica, and going up past the equator to 10 degrees north. This is a plot of salinity concentrations. You can see this tongue here of low salinity water. What's happening is the cold air is causing the water just north of Antarctica to get denser and sink, and as it sinks, it moves northward. So this is like a time machine. This air, or this water here, is in equilibrium with the atmosphere. As it moves north, it ages. So you can look at this water and know what the partial pressure of carbon dioxide was in the atmosphere back in time. So what Peter Brewer did is he measured the CO2 in the seawater, calculated the partial pressure of the atmosphere when that water formed, and got this plot. So as you move from the 50 degrees south up to the equator, you can see here the oldest water has the lowest CO2 concentration, and as we get younger and younger, the CO2 concentration goes up. This is just what you would expect if carbon dioxide was going into the atmosphere, or from the atmosphere into the ocean. So having seen this, ocean chemists, physical oceanographers around the world decided we need to know more about ocean circulation. So in 1989 through 1998, there was two major expeditions. One was JGOFS, the Joint Global Ocean Flux Study, and the other one was WOS, the World Ocean Circulation Experiment, where over 100 scientists from a dozen different nations conducted almost 100 different cruises all over the ocean. Here you can see the legs where the ships went in order to inventory the world ocean concentration of carbon dioxide. They wanted to find out how much carbon dioxide the ocean has absorbed. They also worked in the Indian Ocean, but that figure didn't fit. Let's back up. So we're going to take a look at one section that goes here. It's P16. It starts up at the Aleutians and goes all the way down past Hawaii, past Tahiti, down to the Antarctic. And we're going to pretend we're standing here on the west coast of South America, looking out to the ocean. So on our left is the Antarctic, and to the north is the Aleutians. Or sorry, to the right is the north, and that's the Aleutians. In the top figure, these are the isoplasts of bomb carbon. This is C14 produced by bomb testing in the late 1940s, early 1950s. It's very easy to detect in the ocean because of its radioactivity. And you can see how much of this and where it is penetrated into the ocean. So this is carbon dioxide that's labeled from the bomb testing going into the ocean. The middle figure here is an estimate of the anthropogenic CO2. This started much earlier, so it is penetrated deeper. It's harder to detect, so the signal is weaker. But we can see it's almost down to about 1,400 meters into the ocean in the South Pacific and past 1,000 meters in the North Pacific. So the CO2 is going into the ocean. And this bottom figure is the partial pressure of one of the freons. These are totally man-made chemical. They're very good tracers of time in the ocean. And again, you can see how much they have penetrated into the ocean. It's the exact same pattern. So all these gases are penetrating into the ocean. Now this is a figure from the Hawaiian Ocean Time Series Station. Instead of looking across the geographic extent of the ocean, We're sitting in one place. It's up here called Station Aloha, north of Oahu. The Mauna Loa station that's on top of the volcano is here on the Big Island of Hawaii. So here's the Mauna Loa trend data that I showed you earlier, and you can see the CO2 concentration in the atmosphere is steadily rising. They collected water samples here every month at Station Aloha for 20 years, and that's this plot here. And they measured the partial pressure of carbon dioxide in those samples. Now, because the Mauna Loa data is measured on dry air, when you're taking water samples, it's wet air. And so that humidity is diluting the signal. So that's why the CO2 concentrations are smaller, but they follow the exact same trend. So this rise in CO2 in the ocean is being directly driven by the CO2 in the air. The blue points here is a measure of pH on this scale here. And you can see that as the CO2 in the ocean is going up, the pH is going down. It's not a lot. It's only 0.05, 0.05 of a pH unit. But it's steady and it's ongoing. Now, what's going to happen in the future? Well, the IPCC has made an estimate of what the CO2 emissions are going to be. That's this black line here. Now, they do their anthropogenic emissions in gigatons of carbon, not CO2. Carbon weighs 12 grams, CO2 weighs 44. So we have to multiply these numbers by 3 2/3 to get gigatons of CO2. But it starts here in 2000, so there's 7 times 3 2/3. It's about 25 gigatons a year, and it goes up. By the year 2016, gigatons of carbon, so that's almost 60 gigatons of CO2 a year. That's a tremendous increase. Now what these models show is they said, what levels can we emit if we want to hold CO2 in the atmosphere constant? And they had different levels, 350, 450, 550, on up to 750. And that's why there are these different lines. The interesting thing is, it starts out at this point, we need to reduce the current emissions by 3.67 billion tons of CO2 per year if we want to stabilize at 550. Now remember, we're just below 400 now. So to stabilize at this higher level, we already have to start cutting back on emissions. And this 550 is almost double the pre-industrial level. Now, they say that these levels can be obtained. Now, people that did these models say that these levels in the atmosphere can be obtained by a mixture of conservation, substitution of energy sources, or sequestration of CO2. But I don't see any of this happening. So to be honest, I don't see where we're going to be able to follow any of these lines. I think we're going to go up and follow the solid black line, where we just keep putting more and more CO2 in the atmosphere faster and faster. Now, what happens when you do that? How much of a reduction in ocean pH can be expected? So this model by Caldera and Wickett was published in 2003. Here's the prediction from the IPC, the business as usual prediction, where you just keep making it as fast as you can dig it out of the ground. Here's the atmospheric PCO2. It goes up to about 1,500. And that will give us, at a maximum, a minus 0.7 reduction in surface ocean pH. Deeper down in the ocean, it's reduced because it takes time to mix down and it's slowly buffered. So we can expect, if we keep on going the way we're going, big changes in the ocean pH. So comes the all-important question. Why should anybody care? I mean, the pH shift is small. Even at its worst, it's only 0.7, and in some places it's only 0.3. CO2 is a plant nutrient. Shouldn't that be good for plants? And the changes I'm talking about are 50, 100, 200 years in the future. Why do we care? Well, if you start talking to marine biologists and you start telling them about these changes in the ocean pH, they get very excited. And they start pointing out bad things are going to happen. There are algae in the ocean called coccolithophorids. They build their shells out of calcium carbonate. When you change the pH, it's harder for them to make their shells. They're going to die. If the phytoplankton die, then there's nothing for the zooplankton to eat. And if there's nothing for the zooplankton to eat, there's nothing for the krill to eat. And if there's nothing for the krill to eat, there's nothing for the fish and the marine mammals to eat. The whole ecosystem will collapse. Now that's the worst case scenario that the biologists can imagine. They also talk about the fact that you have reduced fertility. Lower pH, the eggs don't hatch. Larvae don't settle. Polyps don't metamorphose. So different life cycles in different organisms will be interrupted. I talked about the reduced productivity. A couple years ago, Peter Brewer and I wrote a paper where we pointed out that respiration is going to get reduced because high levels of PCO2, of partial pressure of CO2, inhibit breathing. Now, as we're all doing that experiment here today. As we sit here in this room, we're all respiring CO2. As those levels go up, people are going to start to feel drowsy. It's not that we're using all the oxygen in the room, it's that we're putting out CO2. There's also this change in the physics of the ocean. As the pH goes down, sound goes further. It's less absorbed. This has impacts for whales and anti-submarine warfare. Whales communicate by making sounds. Well, if their sounds travel further, maybe they can communicate further. On the other hand, if sound goes further, maybe the din of the ocean gets louder and they can't hear each other. Same thing happens with submarines. You look for them with sonar. Well, if the sound goes further, maybe you can detect the submarines further away. But if the ocean's noisier, maybe you can't hear them because of all the ambient noise. So these are questions that people are working on trying to resolve. So last month in September, there was a meeting in Monterey. It was the third High CO2 World Symposium. The first one was 8 years ago in Paris. About 25 people showed up. The second one was 4 years ago in Monaco, and 100 people showed up. This time, we had over 500 attendees and had to turn people away. The idea of working on ocean acidification and studying its impact has suddenly caught on. We had over 200 contributed papers at this talk, and there were 11 plenary sessions where we got everybody together in a big room and we listened to some common theme talks. Now, the results that were there, they're too numerous for me to summarize right now. A lot of them were biology. I'm an ocean chemist. I don't want to do them a disservice by misquoting them, but I'll mention a few examples here. But there were a couple emerging themes. One was the biologists have caught on to the fact that there are multiple stressors. It's not just the ocean pH and the ocean CO2 that's changing. The ocean's also warming, and the oxygen in the ocean is going down because the ocean's warming. So they're beginning to do experiments where all three stressors are considered at the same time. And because they're all stressors, they have a synergistic effect. So just doing a study on a single stressor, you might think, well, it's okay, the animal's going to be all right. But when you combine all three, they may not make it. So they've learned that they need to start doing these multiple stressor experiments. The other thing that they discovered is that when they do the experiment slowly, there's an acclimatization of the animal. For example, if you take the sea urchin and let it spawn and put those fertilized eggs into acidified seawater that's CO2 rich, not very many survive, much less than in normal seawater. But if they acclimate the parents before they spawn to this low or high CO2, low pH seawater, and then let them spawn, they get much better survival rates. So there's something going on other than the simple experiments that have been done to date. So there's a lot more to be learned. This field is just beginning to take off. Now I mentioned coccolithophores. These are there was one. It's a small marine alga, only 10 to 40 micrometers in diameter. And they build the shell with these little platelets called coccoliths. And they're made out of calcium carbonate. Now remember I said in the beginning that when you add CO2 to seawater, you titrate some of the carbonate there and make bicarbonate. Well, they need the carbonate to make their shells. If you're adding lots of CO2 and titrating the carbonate away, it's going to be harder for these to make their shells. So they're not going to be able to grow as much. They are at the base of the food web. So if you take them away, the food web's going to collapse. On the other hand, they compete with diatoms for nutrients. Diatoms build their shells out of opal, silicon dioxide. So what may happen, we don't know, because the experiments are just being done right now, is that if the calcareous phytoplankton go away, the siliceous phytoplankton, the diatoms, may come in and take over. Now, if the zooplankton aren't picky eaters, they'll be fine. But if they are, if they only want the coccoliths, they could starve. And they've noticed that it only takes a small increase in PaCO2. Now, this is double atmospheric. We're headed here for sure, and triple the pre-industrial CO2 levels. Those cause a reduction in the calcification. So we're getting close. This is an experiment that was done by Shirayama in Japan, where he was looking at sea urchin larvae and looking how they developed in different pH solutions. Now the top series of photographs, he acidified the seawater with CO2, like is happening in the ocean. And you can see the control. This is what the animal looks like when everything's fine. And as more CO2 is added and the pH goes down, the larvae become more and more deformed. If they added HCl, which is a strong mineral acid, and lowered the pH, they got a similar effect. Now, it may turn out that this is the experiment to do by adding CO2, because that's what's happening. Along the west coast, there are a series of oyster hatcheries. And some of them have been noticing that they've had traumatic die-offs lately. What's happening at the sea surface, in 1750, this is what the surface pH looked like. It is about 8.15. And you had coastal upwelling where the pH was dropped to around 8 or 8.05. Coastal upwelling is when water that's deep in the ocean, 400 or 500 meters down, is drawn up to the surface by the offshore winds. Now this water being lower in pH is then mixed with the surface water. In 1750, this water hadn't been acidified yet, so it has strong buffer capacity, and you only got a small drop in pH. They're predicting in 2050, a few years from now, sea surface pH will look like this. It'll be down about 7.9, 7.95. When you have upwelling then, because the surface seawater has already been partially titrated, there isn't as much buffer there to take care of the upwelled water. And so the pH along the coast is going to drop even more, down to 7.8 to 7.85. Already they're seeing problems at the oyster hatcheries when these upwelling events happen right about the time the spawn is ready to settle. They lose the whole crop. And they didn't know what it was at first, but they realized it only happens certain times of the year, and those are the times of the year when they have this upwelling event. And so the oyster spawn is very sensitive to the seawater pH. If it drops too low, they won't settle, they'll die. The other poster child for ocean acidification is coral reefs. Now, healthy coral reefs, they support fisheries. They also support tourism. People come, they go snorkeling there. And there's a lot of money in both industries. If the corals can't make their shells because the calcium or the carbonate in seawater has been taken up by acidification and they die off, people aren't going to want to come and snorkel there. The tourism industry will collapse. If there isn't coral living there, the fisheries won't exist there. The fisheries will collapse. So there's a tremendous amount of monetary impact that could happen should the coral reefs die off. So the question becomes, how much acidification can they take? Where's the tipping point? A few years ago, David Klein did an experiment on the Great Barrier Reef. A group of my colleagues from Mabari went down to help him and set up his experiments. And he set up these open chambers on the reef that allow reef water to flow through back and forth with the tide. And in some of those chambers, he added carbon dioxide to lower the seawater pH. And what he noticed is that the elevated CO2 levels caused an increased dissolution rate in the crustose coralline algae. Coral reefs aren't just corals, there's also algae that grow that precipitate calcium carbonate. And he noticed that even with the small changes that he had, offsets of 0.14 to 0.35, were causing this increase in dissolution. So for coral reefs, we're very close to the point where we're going to start seeing damage occur. I mentioned earlier that Peter Brewer and I wrote a paper on respiration. We took a very simple look at respiration and said, well, basically what's happening in terms of chemistry is you take organic carbon, react it with oxygen, and you produce CO2. This reaction produces the metabolic energy that drives our bodies. If oxygen is low, it's going to inhibit respiration. If CO2 is high, it's going to push back, and that's going to inhibit respiration. We developed a concept called the respiration index to measure this ratio, and I plotted it here with 3 different cases. The blue and the green show, well, the green is the current modern condition. The blue is what we thought in pre-industrial. So you can already see there's a little bit of effect of carbon dioxide penetrating the ocean, shifting this index. If you were to equilibrate the whole ocean with twice the atmospheric concentration of CO2 that we had before the Industrial Revolution, it would shift the index to here and 3 times here. So this is making it harder to breathe. The respiration index plots are in this graph, and you can see the index is getting lower and lower in the core of the oxygen minimum. So it's even harder to breathe there. But the zone is also expanding upwards and deeper. So when you have animals that like to migrate into the deep water in the daytime to get out of the light so they don't get eaten, they're going to start seeing this impact here at shallow and shallower depths. Now, when we wrote this paper, our friends that are marine physiologists didn't quite like it. They objected that we were being much too simple, and they didn't really think this was going to happen. So we did an experiment out in Monterey Bay. We took one of the detritus samplers, and this is just a plexiglass chamber with the top and a bottom that we can open and close. We've got some pumps here. We've got a CTD for measuring temperature and salinity, and we've got another pump that we can inject CO2 with. And what we're going to do is we're going to capture a small squid that's living close to this oxygen minimum. So he's got low oxygen already and high CO2. And we're going to add enough CO2 to push him 100, 200 years into the future and see what happens to him. Okay. And there's the little guy right there, right after we caught him. The way you catch him with an ROV is you open the top and bottom, And you try and sneak up on a little squid with a 4-ton vehicle that's got bright lights and loud motors, and the pilots get very sneaky. And, so they'll come in below it, and then they'll pop up with the ROV, and when he gets caught inside the chamber, they close the lid real quick. Where'd this go? Okay, so he's in the chamber, he's swimming around. We gave him a few minutes to get used to it, and he quickly realizes he can only go so far. But he's swimming around, and very relaxed, and not too aggressive. And right about this point, we start to add the CO2, and it takes a few minutes to mix. So there's a break in the video here. And now he's been in the CO2 for just a minute, and already he's on the bottom of the chamber. You can see he's inked as a sign of distress and an escape mechanism. His body colors are flashing back and forth. He's really upset. You'll notice his tentacles, instead of being in the normal swimming posture, are all splayed out. After a few more minutes, he just lays there totally still. He's totally exhausted, all his metabolic reserves. He's probably close to dying at this point. And it didn't take much CO2 to do this. So our basic idea about the CO2 affecting respiration and affecting marine animals is pretty dramatically shown here to be correct. Now, we did take pity on this guy, and shortly after this, we opened the top and the bottom of the chamber and let him fall out. After about 20 or 30 seconds, in normal seawater, he revived and swam away. Okay. Now, we've also been doing other small-scale CO2 experiments at Mabari, trying to understand. Now, some of these, where we look at the kinetics of hydrate formation and the rates of liquid to and hydrate dissolution, only chemists are interested in there. And we actually, the videos from these experiments, we've actually won awards for having the most boring video that year. Because we actually did an experiment where we sat there and we watched ice dissolve, the CO2 hydrate dissolve. It took a day and a half. Not real exciting. But we've also been testing some ideas about deep ocean CO2 sequestration and working with marine biologists. Now, the CO2 sequestration was an idea that was proposed in the early 70s when people first thought about global warming. They said, well, you know, if CO2 is going up in the atmosphere is causing this, and some of the CO2 is going in the ocean anyway, why don't we just put it in the ocean straight away? And so they had ideas about these collecting CO2 from factories and liquefying it, taking it out with ships and pumping it into the deep sea. And we said, well, wait a minute, maybe we should do an experiment and see what's going to happen. Now, there are some problems with doing this because we have limited control over the experimental conditions. But we went ahead, did it, and we observed some pretty novel results. In the first experiment, we just went out and took a 4-liter beaker, set it on the sea floor, and we filled it halfway with liquid CO2 to see what would happen. The guys that were talking about putting CO2 and sequestering in the ocean said, well, it's going to form a hydrate, it'll skim over like ice on a pond, and it'll just stay there. It formed hydrate all right, but what they didn't realize is the hydrate was denser than the CO2 at that point. And the hydrate sank to the bottom. And as you form, the hydrate reacts, each molecule of CO2 reacts with 6 molecules of water, so it has a bigger volume than the CO2 you start with. So the hydrate was sinking to the bottom, and it pushed the unreacted CO2 up and out the top of the beaker. I'll show a couple videos of that in a minute. The other thing we did is we said, well, maybe that's because of the shape of the beaker. So we got these corrals that are about 30 inches across, but only 6 or 8 inches tall. We'll fill those up with liquid CO2 and see if it behaves differently. Well, it did. It sank down into the mud, formed hydrate there, and we got these large crystals of CO2 hydrate erupting out of the ground, like the frost heaves you see on the roads in New England in the wintertime. But what was really puzzling to us is an identical corral, just 10 meters over to the side here. The CO2 did absolutely nothing. It sat there. So we discovered that the behavior of liquid CO2 in the deep ocean is very erratic. There are some very fine thresholds that we don't really understand that cause it to go and do different kinds of behavior. So I got some video clips from this beaker experiment. And in this first one, you can see the liquid CO2 is very slowly being pushed out the top, and it spills over and falls to the seafloor. Now, it looks like it's in slow motion, but this is real time. The density between the liquid CO2 and the seawaters, that density difference is very, very small. So it almost floats. And, sorry. This went on for quite a few hours. This fish came along. He was very inquisitive, and we thought for a second he was going to eat the liquid CO2. So there was a lot of screaming and hollering in the control room, trying to convince him not to. I guess he listened to us. Now this experiment we did at 3650 meters in the ocean. So it's almost 2 miles deep. The temperature down there is 2 degrees centigrade. If you go shallower, the liquid CO2 actually floats. And then there's this video clip of the droplets of CO2 rolling along the seafloor. And it runs into this little sea pen here, goes around it, and forms back together. This was about the time the Terminator movie was coming out with that guy that was a liquid metal, and we're looking at this one and just exactly what we've done. Now, when we first showed these videos at science conferences, we got some really strange comments. Our chemist colleagues said to us, well, my God, you're going to change the ocean pH doing this. We had other colleagues that said, we didn't know there was fish down there. So there's a lot of unknown about the deep ocean that really needs to be gotten out to the public. Now, I said we started out with some small experiments with CO2. Most recently, we've gone to a bigger experiment where the biologists want to look at animals on the deep sea floor. So we built this chamber here. The lid here in the middle is about 1 meter square, so we can put experiments in. And the idea is we're going to run water through this that we add CO2 to. Now, we've made it double-ended because there are currents on the seafloor that go back and forth, and we didn't want to try and push against those currents. We had to add wings. If we add the CO2 to the seawater here, it takes a while to react, and these wings have a little maze in them so that it has a long path for the CO2 to react, so that when we get into the chamber, it has the pH that we want. There's a control computer in this pressure case, and there's a series of pH sensors on the front and back. There are fans to drive the water through. And these white boxes, this is syntactic foam. It makes the thing float in seawater so we can get it back when the experiment's done. There are 4 places where we put lead weights on. We put 4 50-pound weights. Adds 200 pounds. It makes it 100 pounds heavier than it needs to float in seawater, so it sinks. And at the end of the experiment, when we pull these weights off, it'll be 100 pounds buoyant, and it'll come back to the surface. So here's the experiment. We fold the wings up, and we've dropped it from the side of the ship. We just take a crane, put it over the side, open the hook, and down it goes, and you hope you find it. It's sitting on the seafloor out here in Monterey Bay at 890 meters water depth. This is where the Monterey Area Advanced Research Site is. There's a underwater observatory there where we can plug in and get power and communication. And once we've plugged in and powered up and we know everything's working, the pilots on the ROV fold off the arms and we're all set up to do the experiment. Now, those early experiments with CO2 may have had uncontrolled results and been hard to reproduce, but we did learn during that time how to deliver CO2 to the seafloor. And what we do is we connect a CO2 mixing box up to this system, and we load that up with 200 liters of liquid CO2 so we can run the experiment for about a month. And our first experiment happened this past summer. Jim Berry was studying the feeding response of sea urchins, and he put a series of sea urchins in a box with little channels and put kelp at the far end, which is their normal food, and watched to see how fast they would go in this system here where they were in CO2-enriched seawater, and he also did it in a control experiment where it was just regular background seawater. Wasn't really exciting. It took 3 days for the sea urchins to make it from one end of the chamber to the other. And they didn't really see a change in their feeding response due to the CO2 enrichment. That's the state of where we are in terms of doing research. At the end of these talks, I like to sort of give a little something positive. And but given all the things that are happening about CO2 and the rate of its growth, most people think it's a pretty hopeless case. But I just want you to remember it's hard to make predictions, especially about the future. If tomorrow somebody discovers a new source of energy that's CO2 free, we may not have this problem. If they don't and we continue on, we most certainly will. Roger Revelle, who was Dave Keeling's mentor and encouraged him to do a lot of his CO2 research, he said, we are doing the experiment. So even though we don't know what the future is going to be like, we're actually going to do the experiment with all this industrial CO2 being released, and we will find out what happens. It's just going to take 100 or 200 years. Lastly, there's this quote from Max Planck. An important scientific innovation rarely makes its way by gradually winning over and converting its opponents. What does happen is that its opponents gradually die out and that the growing generation is familiarized with ideas from the beginning. And that's why it's so important that so many people here tonight are young people. It's your generation that's really going to be able to do something about this. My generation, we're set in our ways. We rarely change our minds about something. As you grow up, you're going to know about ocean acidification. You're going to know that it's real, and you're going to have an opportunity to deal with it. And at that point, I'd like to say thank you.